Thanks for coming. We can go ahead and make a start, I think. So my name is Charles Feddersen. I'm the Group Product Manager for Postgres on Azure at Microsoft. That manifests in a few different things. It's our managed services that we run in the cloud, Postgres Flexible Server, and Cosmos DB for Postgres, which will be the core of this discussion today. And then also the teams that make contributions back to the open source community, both Postgres and Citus, which is a Postgres extension that enables distributed query execution, which is actually the underlying technology that's going to enable a lot of what we talk about and what I show you today. The topic I picked to talk about on Postgres, and I'll remind everyone that we're talking about Postgres here, we're not talking about SQL Server, is that how to build distributed OLTP applications using Cosmos DB for Postgres. Distributed systems in and of themselves are not new things, but distributed OLTP has always been a tricky thing to achieve due to the sensitivities of latency that we're looking for in these apps and the challenges of networks and things like that. Everyone's built on single machines. And so today in the session, we'll talk a lot about the architecture of these things. We'll run a ton of demos, both load and functional, and really just give you a sense about how you can build these things scalably using Cosmos DB, and simply, I should point out. Okay, so the agenda today, we'll talk about distributed OLTP, what it is, how we got here in the history of technology. That will represent about one slide. We'll talk about the myth of distributed databases. I won't tell you what the myth is now, but it is prominent and it is wrong. And so we will address that head on. We'll get into how we build these things, how to fix them when they slow down. I'll talk a little bit at the end just around the feature set of enterprise readiness within Cosmos DB so that you're not left thinking, wow, this is super scalable and great, except it's got no security and it's completely useless to me. And then I'll just wrap with a few getting started resources at the end. So let's get into distributed OLTP. What is it? So relational databases are omnipresent. They've been with us forever, right? Everyone's been building on these things for 20 plus years easily, right? But we always built in effectively a single node architecture. There were all sorts of tricks for scalability. There were read replicas, there was transactional replication. There's all sorts of capabilities, but fundamentally, if you wanted to insert a record or create a table, you connected to one machine. That was the master, if you will. Then NoSQL came along. With the advent of the internet and click tracking and what have you, we basically threw out all of those relational properties that we know and love and trust. Foreign keys, don't need them. Unique indexes, forget them. Just give me something that horizontally scales forever that I can write something to, typically a JSON document, get it back out really quickly, and effectively power the internet. And so there were different form factors of that. What's happening now is that the business applications, or as Savannah talked about in the previous session in this room, SaaS, software as a service applications, are exceeding the scalability of a single machine. But they still need the relational properties that we know, love, trust, and depend on in any relational database, regardless of whether it's Postgres, SQL Server, or anything else. And that's where distributed SQL comes along. It enables a single endpoint, just picture a server name in a connection string, underpinned by a few or dozens of compute nodes that are operating on an OLTP-based workload over a sharded, shared nothing architecture. And that's the trick for achieving scale. And so what does this look like in the real world? On the right-hand side, you've got perhaps the most traditional definition, or maybe slightly overextended definition, of scale-out. A single master machine that could typically represent 100 or so virtual cores, handling all of the writes, definitely, any table or DDL statements, and then occasionally a degree of reads as well. And then scaling out of that is a set of replicas. These replicas could be synchronous, which means that you'll read exactly what you just wrote. That has some latency implications on the read, because it's got to commit over to the secondary before the transaction will complete. Or it could be asynchronous, which is very commonly used in internet traffic. If you ever wondered why you go and update your status in like a social network and then you don't see it for about 3 or 4 seconds, that's just asynchronous replications at internet scale. And that's what enables me to update my stats quickly and then just let it gradually propagate out to the rest of the world. And that has trade-offs as well. On the right-hand side is what distributed OLTP on a cluster looks like. In this form factor, you have a single connection string only. There is one place to connect to, but then we will fan that read and write workload out across a set of nodes where the data has been architected to shard across those clusters. There are different ways to shard. We'll talk about that a little bit today. But the beauty of this is the simplicity, that your application still only talks to one endpoint, and the scalability that you can just continue to add nodes and rebalance that data. And so long as your data model is architected nicely for distributed systems, that thing will just scale magnificently, from dozens to even hundreds of nodes without any issue. So how does sharding work? This is my most rudimentary example. It may be the only slide you see at SQL Bits that actually has some mathematics on it, so we're going to go relatively slowly on this guy. What you can see on the left-hand side is a table. That table has got it's got 4 columns: cust, order ID, an amount, and the shard ID. And imagine that I'm loading this from a file into a table that has been predefined to shard on the cust ID column. I have in Cosmos DB for Postgres, the default number of shards, you could think about these as 32 physical tables. You only see one, but we're breaking it into 32 tables. The default is 32. And so every row I insert needs to look at the customer ID value and determine which of the 32 shards or buckets I'm going to put that in. The simplest way, this is not the actual sharding function, but the simplest way to show this is with modulo operator, which is the percentage. So if I take 543, for example, and I modulo 5 that, I'll end up with 3. The remainder is 3. Then because I'm not base 0, I want a base 1, I'm just going to add 1 to that. And no matter what I do, ignore the 32 default I just told you, in this scenario, no matter what integer value I give that, the answer from that function is going to resolve to a value between 1 to 5, guaranteed. Now, if I give it a string, I could checksum it. That could be a positive or a negative number. I can then absolute value that. I can modulo it, and I'm still guaranteed to get 5. So it doesn't matter the data type. You can put any data type in a sharding column, we will handle it. For a really simple example, I'm giving you an integer, and there's no integer on the planet that when I run through that function won't resolve to a value 1 to 5. Now, once I put that in the bucket, there's a second thing, which is the row at the very bottom of the slide. Every identical value or every customer ID of 543 is guaranteed to land in shard 4. That is the magical guarantee that we depend on for scalability. That means that as I start to think about whether it's a multi-tenant app or some of the ways the query optimizer handles processing queries in the database, and I'll show you, it can trust that 543 is always on one node only. The simple optimization we get is if I've got a cluster of 100 nodes, it's all running under one connection string, I say, give me a count star where the value equals 543. Cosmos DB is smart enough to send that just to one node. 99 nodes will be untouched. And when you think about the scalability of that, of tens of thousands of queries, each asking for a different customer ID, statistically that balances very cleanly. And I'll show you that towards the end of the session as well. So the great database myth, the great distributed database myth is that distributed databases are only useful for large data volumes. The sheer number of times a customer said to me, Charles, this looks amazing, but I don't have enough data to justify this, is absolutely insane. When you add compute or when you build a distributed system, you are actually getting 4 things. You are getting more CPU, you're getting more memory, you're getting more IOPS because it's shared nothing storage, and you're getting more disk space at the end because we attach disks to each node. Anyone who's spent any time building database systems, which I'm going to assume is pretty much every single person in this room, has encountered scenarios where you've had a small amount of data with a huge workload and your CPU is just melting and you've got nowhere to go. Or you've had scenarios where you've got a small amount of data, but the workload is touching nearly all of that data and your cache hit ratio is very low. And so you start thrashing the disks because you can't fit enough in the memory. And then the CPU starts stalling out and it's not doing much. You can have a write-heavy workload, which is going to exhaust your IOPS, but actually is not that CPU or memory intensive at all. So it's really easy actually to write. I could write an artificial workload in any relational system that would exhaust one component of that stack only, And so the ability to scale out efficiently gives you all of those resources in a near linear manner to build out these scalable systems. And so the thing, if you take nothing away from this session, please know that distributed systems are stunningly powerful for scaling any bottleneck in the system. And the demos that I'm going to show you live today are actually running on only 100 gigabytes of data, right? But I'm going to blow up the system a little bit while we're doing it. And so I talked just now about how we get more CPU, how we get more memory, how we get I/O, right? That solves the compute problem. But there's another scalability challenge in relational systems as well. For example, the queries. When we shard queries, as I mentioned, we can eliminate only onto one node. We can reduce the I/O. When we're running single-threaded operations like updates on a distributed table, that will now run 32 updates concurrently on one 32nd fraction of the data. And I'll show you a visualization of what that means in a second. Or if I've got maintenance operations, right, like I'm doing a backup or I'm creating index, all of these things will run, by default, 32 times faster because we run 32 of them in parallel, one on each shard, and then drop them, or if it's an index, it goes in the database. If it's a backup, we drop it out to cloud storage, right? And so the scalability of all of these operations in a distributed system starts to get very nice. Here's an example of memory, for example. On the right-hand side is Postgres Flexible Server, which we ran, I think this is the TPCC benchmark, so it's orders per minute, and it was intentionally run to fractionally exceed the in-memory capabilities of the machine. Right? So we made Flex look bad, but this is a reality of what happens in the real world. On the right-hand side, you can see we got 15,000, almost 16,000 orders per minute with a latency at the top of 368 milliseconds. Right? Not bad, but not great. When we switch that to a distributed cluster, right, Cosmos DB, it's all Postgres, by the way, we were able to bring that working set back into memory. When you go from a single node to 4 nodes, what actually happens is you go to 5 nodes, because there's 4 worker nodes and there's a coordinator node at the top, right? But what happened is because we brought the working set back into memory, we now get a throughput of about 214,000 orders per minute on a latency of 39 milliseconds. The bullet, actually, which I don't have on the right-hand side, is key. I can tell you this. 5x increase in cost, sure. 13x improvement in performance. Better than linear scale when you keep the working set in memory. Again, customers, clusters, lots of servers, sounds expensive. It is a little more expensive. It's multiple machines. But this is a proof point about why it can be so important to keep that working set in memory. And how easy it is to do it in Cosmos DB, because if I ever saw those numbers peeling back on the right-hand side, I just add another node and keep going. This is what a parallel update looks like on the exact same machines that I described in the previous slide. The top blue bar is the single node update, and then the green is Cosmos DB. This is precisely timed in PowerPoint, right? Rather than crack out. This is how long the update literally took. I set the timing on the animation precisely to the query execution time. Cosmos DB finished before I even broke out my first sentence there. And now we've finished the single node as well. This is the same update statement, text for text. There's nothing magic about update this shard and this shard and this shard. There's no parallel keywords or anything. You lift up an app and you bring it onto Cosmos DB, you get the parallelism out of the box. So let's take a little look at how this actually works. At the top is just I've shorthanded a really simple create table, sales transactions table. That's a 2-step process to creating distributed tables in Cosmos DB. The first is the top statement, which is just a vanilla create table statement. Everyone here can write those in their sleep. The second is the function. It's a function built on the Citus extension, right? And what that does is create distributed table where I give it the sales transactions table name as the first parameter, and the column, which is customer ID, which I sort of borrowed from the previous example a few slides ago. This gives me my 32 shards. Now, I keep saying 32 shards is default. You can remove them, you can add them. Obviously, with 32 shards, the maximum cluster size you can get to, which is any use, is 32 nodes. We have customers actually that are running significantly more shards on more nodes. But that's an interesting sort of point as to how this works. Then I come to insert some values. So here, insert into sales transaction, cust ID, that's my distribution key. That's the one we're hashing using our sort of modulo demo function that I showed before. and code, which is nothing. It's just a varchar, it's called code, and that's it. What you'll notice here is that I've tried to illustrate visually what would happen if I was inserting these into a non-sharded table and a sharded table. The non-sharded table, everything goes into the same table, obviously, right? The sharded table, I don't know if the values 1 and 2 will exactly go into shard 2 and 5, but statistically they're going to land in different shards. And that's the point that I'm making here. And this is how you get that scalability. Again, that is the actual SQL statement. There's no insert into shard, fancy keyword. The distributed query engine in Cosmos DB will handle the routing of all of the data for you. So you don't worry about multiple connection strings and all sorts of stuff like that. And then beyond that, to show how this sort of hierarchy works, multiple shards will exist in one or many nodes. Now I want to make a really important point here. With Cosmos DB, you can start on a single compute node. Conceptually, we completely, or physically, we separate the notion of distributed compute and distributed data. What that means is that you can have one node, super cost effective, it could be 2 cores, it could be a burstable SKU, and on that, you can create a distributed table. You'll get 32 shards, they all just live on that one machine. What I tell anybody building net new apps on Cosmos DB to start cost effectively is build on a single node to start, but build a distributed data model from day one. Because what that means is when you go from 1 node to 4 nodes, you add the compute, you run a single statement to rebalance, and because you've already got a distributed data architecture, it just rebalances and you're off. Right? Now there are some trade-offs to distributed systems which we'll get to in a second as well. But my general sort of position here is that if I'm building a net new app today on Postgres in the cloud, I should always go to Cosmos DB because I've got room to run on scalability, but I don't need to start there. So the hierarchy actually looks like this. There's a couple of ways you can squint as to the shard table one, but just to give you a general high level, clusters have nodes, nodes have shards, shards have tables. That's basically the way to think about it with respect to the hierarchy. I want to quickly just walk through deploying the cluster just to make this a little bit more real and add a little bit of concept, practical concept to what I talked about, and then we'll get into some real demos here. So if I'm deploying Cosmos DB for Postgres, it's in the famous now 6-tile interface of Cosmos DB. And so we've got NoSQL, Postgres, Mongo. We go ahead and take PostgreSQL, and I click through a little bit here. I give it the resource group and everything you're familiar with. But what I want to point to is configure. So here we've got 3 key concepts: node count, node size, and storage size. 3 different axes of scaling the cluster. So let's start with node count. I mentioned already you can start on single nodes, but we're doing big demos, so that's kind of boring. So we'll go ahead and we can take like 4 nodes, for example. This drop-down, which doesn't fit on the slide, goes to 20 nodes. It's a soft limit. We're actually going to lift that limit to about 40 nodes shortly because there's a number of customers that are just hitting this one out of the box. But theoretically, you can go significantly larger than that as well. No one ever starts that large, of course. Again, to my point about having runway to scale, this is an important element. So we take 4 nodes. Now we might want slightly larger nodes. So we can go ahead and take 16 vCores here. And then I can go ahead and add up to 16 terabytes of storage as well. We'll just take 8 terabytes here, right? And so the point is that different workloads are very different, right? We know this. They have different pressure points. Some will do better with more nodes with smaller compute. Some may have more analytical functions in them where you need a bigger node. You're doing some really memory-intensive queries, big memory-intensive runtime sorts, big memory-intensive hash joins. And so you've got some choice. A great example of fanning out on smaller compute is like IoT workloads, which are really write-heavy. Low CPU, they need the IOPS. And so you've really got the flexibility on how you want to configure depending on the nature of the system. And inevitably, you're going to get it wrong sometimes as well, and you can always change it also. But if I sort of revert back to where I was before, that sort of gives you a sense of the hierarchy and how it comes into practice when you're actually deploying. Okay. Let's get on to building some of these distributed apps. So if built well, the scalability of distributed databases is what I term, in a completely non-scientific way, magical. Right? Because it will just go. If you get it right, that whole thing about, oh, we're running a scale, we need bigger machines, I go turn up the VM, this thing will just scale out. And I should point out at this point that scaling out and adding nodes to the cluster is a completely online operation. Customers do this in production today. They scale out, and it just keeps running. Online in the sense of reads, and online in the sense of writes. So there's not even a, hey, we're going down on write workloads and you need huge timeout and retry logic in your app. You should do that anyway as a best practice, but we will scale this regardless. Virtually linear scalability. If that data model is well sharded, and we'll get into that in a second, it will just keep going. Now you get to 32 nodes and you're gonna have to do some shard splits. Sure, that's online as well, right? But it'll keep going. You get this predictable and balanced performance across nodes. You always get that to start. It never stays like that, and I'll show you how we can fix that as well. We can maximize the local execution on compute nodes, which we'll get into in depth. That is the scalability trick. Localizing as much, if not the entirety of a query on each compute node. At the end of the day, a distributed system is nothing more than a very scalable and fleet-managed version of single node systems. The network is your killer in distributed OLTP, and I'll show you how you can avoid it. And then you can see I basically made that point at the bottom. However, I've also seen it done wrong. And not only does it waste resource, the more you scale the cluster, the worse it actually gets. And so get it right from the beginning. 5 simple steps here, and I think it'll do well. At this point, I've spent the whole time talking about sharded tables. 32 shards, 5 shards, modular functions, but there's actually 2 types of table, 2 different table types in Cosmos DB. One is the distributed table with the sharding column, and then the other is the notion of a reference table. Why is this important? Because in a lot of data models, not every table has the same column to shard on. If they do, and there are some by the way, it's wonderful. Same type, guarantees the same value in every node. Those joins are going to work perfectly. But sometimes you need to reference table. Reference table means that the entirety of that table is stored on every single shard or every node, right? And so when you write a join, one side of that join exists on the node. What are great candidates for these tables? Well, obviously, smaller tables. Tables that don't get modified too often. Why don't we want to modify these tables too often? Because we need to keep them synchronized perfectly across the cluster. If I insert into a sharded table a single row, I will find that node that owns that data and insert it in a few milliseconds. If I insert into a reference table, I will insert it into one and all the other nodes. And when I've got commits across all of them, I will come back. It not only takes longer, it is more variable as well. I'm not to say you can't do it, you shouldn't do it, you always need to do it. But if you're building high throughput OLTP, you want those high throughput tables to be the sharded ones, which is often the case. Things like sales transactions, inventory management, orders, those kind of things are big, lots of rows, and what have you. You'll also notice that although I've put precisely 500 rows on each of the reference tables in blue, I've said about 2,000 rows of my 4,000 row set in purple, because it's a sharding algorithm. It's not a round robin where I'm guaranteeing to put one here, one here, one here, one here. Right? It's actually looking at the actual values. A well-balanced sharding column will work well. If my shard column that I was using here had one value only in it, then I can guarantee you that all 4,000 rows will be in one shard. That's the guarantee that works for us. It works against us when we have significant skew in the data as well. Things like order ID are great sharding candidates. Things like country are bad sharding candidates. So that's a way to think about it. All right, now we're going to get into some examples. What I'm going to do here for the next 10 or so minutes, I think, is show you a couple of samples on slide and then run the equivalent in code. So it's going to be a little bit of an Alt-Tab party, so bear with me, but it'll be exciting, if nothing else. The first one is filtering on the shard key. I talked about this already. So I'm going to create table here, customer T. I'd shard that on CID. I'm using really abbreviated column names because that's all I could fit into the column headers on each of the table examples in the slide. So we'll call it customer ID, but that's why it's so short. And now I want to count where customer ID is 1. Remember, we guarantee that a given value of a shard will exist on the node. And so that shard2 green box represents the fact that I'm only hitting shard 2. So let's go ahead and take a look at that one. Let's Alt-Tab our way over to good old PG admin over here. which is doing something. Oh, hold on a second. I may need to, oh, that's not coming up. Let's do this. Oh, this is going to be fun. Okay, I can't actually see that, so I'm going to switch to duplicate. Okay, we're good. All right, so here are my architecture demos. Let's go at the top. Demo 1, we're going to blow all these away. PG Admin is, for those who haven't seen it, the SQL Server Management Studio of Postgres. For those of you who long for and miss your user interfaces from the 90s, this is the app for you. So we're going to delete those. Let's go take a look. I've got some other tables here which I'm going to use for a separate demo later, so I'm filtering those out. But Citus tables is the view that shows me my distributed tables, and I have none. Good place to start. Let's go ahead and create customer T. It's got a few columns. It's got a primary key. I put a primary key in there to show that we're not working on distributed NoSQL, Cosmos DB. We're working on relational. And then I'm going to go run this query again. My table's still not there. Of course it's not. Remember, it's a two-step process. I've got to create the vanilla table first, just using rudimentary run-the-mill Postgres syntax, and then I run the function. So let's go run that here. Pretty quick. Let's go run this one. Beautiful. Now I have a distributed table. Wonderful. It's got 32 shards, which you can see right here. I'm going to go insert 3 values. Now, I don't know where those 3 values went. I know that I've put, a shard on customer ID. Here's customer ID. I've got 2 different customer IDs, so they've probably gone into at least 2 shards, but I have no idea where. And now I'm going to run this explain. So here, I'm just doing a count star on the distributed table. Without getting into the nuts and bolts of Postgres query plans, the magical number which you need to squint at on row 3 is 32. I've got 32 shards. How do you do a distributed query to count this table? You issue 32 counts, and you get 32 scalar values back, and then you'll sum them up, and that's a distributed count. It's one of the most wonderfully scalable queries you can run in a distributed system. But I told you that if we filter on the shard ID, we're going to be far more efficient, because those 32 shards have hit all the nodes in my cluster. And most of them did nothing, because I've only got 2 different values in my shard key. So we're going to run this one, and now, to squint right there, task count 1. Because that query's come in, it's run my sharding hash function on the predicate on the way in, said, okay, this is the shard where value 1 lives, and it just routes it there. No change to your app. No multiple service, no connection strings, no anything, right? It just scales. You add nodes. Like I said, we add nodes online while your app keeps running because the connection string doesn't change, no manual routing on your side. So this is a rudimentary demo. Let's go back to, and I think I'm going to break out of this quickly and then switch to, let's just go back to projector mode. That was relatively painless. Okay. Here's the second one, primary and foreign key checks within a shard. This is super important. We're using relational databases because we want referential integrity between our tables. It's a fundamental requirement. And so, create table customer T again, create sales transactions, both with the column that I'm showing here, TID. Alter the table and add a constraint for the foreign key between TID, and actually use CID as well, but in this case, use TID. Within the shard, this works. Within the database, this works. Why does this work? Because my foreign key is between TID and I'm sharded on TID. So 2 tables, remember the guarantee. The query and the database engine know that both sides of that integrity check will be in the same shard because it's the same column, it's the same data type that I'm creating the shard key and the foreign key to. However, what happens if I do it wrong? Well, you can imagine, if I put one of my tables on CID, I cannot create this foreign key check, and you don't want to. This is not a missing feature. If you go and say, okay, I've got a table which is like my customers, I'm going to shard that on customer ID. That's great. That'll probably balance nicely because the customer table is probably full of unique customers. And then I've got an orders table. I'm going to shard that on order ID. Great idea, right? High cardinality, really balanced, going to shard beautifully. If we enabled you to create foreign key checks across the nodes, that means every time you insert an order for that customer, you've then got to go find the node with the customer ID on in the customer table and do that cross-network check. Once, fine, right? It adds maybe 100 milliseconds. Let's do 10,000 orders a second. You've all of a sudden gone from 10,000 in-memory lookups on each of these nodes independent of each other to 10,000 concurrent network connections thrashing each other across the node. The worst design possible. You don't want to do this. There's no reason we can't build this into the system, by the way. We opt not to because you really don't want to do this. And if you really do need to do a check between two rows, just write the code for it. Right? Just say, hey, look, if this exists in this table, then I'll put it there. Right? So it's achievable, but we're not encouraging it by building the feature to support it. Okay, let's switch and go take a quick look at that demo. My apologies for needing to flip around like this. Demo 2, we'll clear it out. Go look at our tables again just to prove that everything's gone. It is. Wonderful, so we're starting fresh. Customer T. We distribute it. Because these are all obviously metadata operations, they're stunningly quick. We'll go check. Good, I've got a table. I'll take sales transaction as well to be the other side of my check. We'll distribute that. Let's just prove that we've got two tables. Wonderful, there they are, customer and sales transaction distributed on different columns. You can probably guess where I'm going with this. Let's go and create a foreign key. I'm going to use a composite foreign key between these tables. Fail, because my tables are not shard aligned. I'm trying to create this between tenant IDs and I'm not sharded equally. Fortunately, super simple to fix. I'm going to alter my customer table that's currently sharded on customer ID, which you can see here, and I'm going to convert it in place to being sharded on tenant ID. Simple. I could alternatively, to make this work, make it a reference table. That would put the totality of customer on every node, and of course that reference is going to just work. We're going to take a look at this. Great, distribution column is aligned. Try to create the same foreign key. Bingo, no problem. So it's doable. We just block the ways that you shouldn't do it by design. In the interest of time, I'm going to accelerate a little bit and go straight into the other demos as well. What about a distributed unique constraint? This one's not too bad, easy either. Let's go drop inventory because I'm going to use that here. And here we're going to go create the inventory table. And I'm going to create distributed table inventory on tenant ID as well. And we'll insert a few values into inventory. We'll check inventory. 3 tables, all distributed on tenant ID, beautiful data model. Tenant ID, you can probably see where I'm going with this. Multi-tenant apps are a great candidate for distributed systems. Every table has a tenant ID, multi-tenant software as a service apps. That tenant ID is the same data type. Every customer has the same individual tenant to them. In your app logic, you will need to handle filtering on the tenant. But we've actually built, and I'll show a quick demo video towards the end, some first-class tenant management features into the database that enable you to effectively rebalance the workload, not just on a per shard basis, but on a per tenant basis as well. But we'll get to that. I'm jumping the gun on that one. All right, alter inventory. Let's go add a constraint on the tenant ID column. Remember, we're sharded on tenant ID column, right? I got a good feeling about this. We'll go run this. Beautiful. Why does this work? Because we guarantee that a given value will stay in one shard and therefore it will not exist in any other shard. The database has not checked for the unique constraint everywhere. It knows that I've got a unique set per shard. Super scalable. 10,000 nodes is as scalable as 2 nodes because we're going to create a unique index and check that index within each shard or each node. However, I'd really like to have a unique index on the inventory ID. This will not work. This is probably the least scalable thing you can do in the system. I have 100 nodes, big system running, tens of thousands of orders all the time. And I've got a unique index. I'm permitted to create a unique index on the non-sharding key. I want to insert 1 record into that orders table, and I need to spin up 99 connections to all the other 99 nodes to check if that is. I'll go do non-clustered index seeks on all of those tables. I'm taking compute resource, I'm taking network resource. Don't do this. So we don't let you do it, as you can see right here. It's just not scalable. There's no good reason to go do this. But at the same time, be aware of the fact that we have depended on multiple unique constraints in large tables for a while. This is one of the great, I would say, trade-offs in distributed systems versus single node systems. The size of the trade-off is probably subjective depending on who you are and the pain that you've had with databases in the past, but I think it's an acceptable one for the scalability benefits that you get in the system. Okay, and I answered that question already. The answer is it would be bad. So let me go back to projecting again, because I think I've made up a little bit of time here. And we'll just drop out of, oops, no, we can do it like this. So this is the one that we just talked about, right? Unique indexes on the tenant ID works great. Unique indexes on the non-sharded column works bad. Don't do it. Fortunately, you can't do it. What about joins? Now, joins are a little trickier, right? Because joins are a sort of query runtime thing. Sometimes they're important. So we permit you to join across nodes. However, you do need to manually enable it in the cluster. We've had a bit of feedback to say it should be on by default. I could go either way on this one, so maybe we'll go do that in future. But today, you need to turn it on. But with the join, again, what we aspire to do is push as much of that query down into the coordinator as possible. So imagine that count star I did before, where I said count star the most scalable query. We just run 32 parallel count stars and sum them up. What if we had like join table A, B, C, and D, where filter, we'll do some window ags, it's an intense query. The dream of that is to push all of those joins locally onto each node with no data movement. And so more commonly, you'll see this in analytics and warehousing patterns. Big star schemas, again, reference tables, distributed tables, localized star joins, and then bubbling up to a global aggregate at the top. But in this example, you can see that I'm creating customer and sales transaction, and then I'll do a query where I'll join them on the tenant ID. Beautiful, localized join. And although there's not a where clause on this query, my blue background there is basically indicating to you that I can achieve this query on a single node. And so that is wonderfully scalable. Alternatively, like I did before, I showed you the count star. This is sort of the HTAP scenario. There's tons of great replication technologies out there for emitting data from operational systems into analytical systems to do analytics there. They are a great approach, in my humble opinion, because data warehouses or big data systems or what have you are designed to effectively centralize a lot of different operational systems and bring that data together. The trade-off, of course, latency. Asynchronous replication. If you think it's bad enough to have a commit between two nodes in an operational cluster, imagine if you had to commit a record and commit it to the analytics system before that OLTP transaction finished. Absolute no. You're into seconds at that point, easily. And so the reason that HTAP is interesting or valuable for these fan-out queries is this is really the only way to ever get the global, transactionally consistent state of an application. When I run this query, I will see to that transactional point in time what's going on in my operational system. I can't see anything else because it's not my data warehouse, but that's why I see in many cases, even though people will sort of squint at architectures that have sort of frayed over time, where analytics got pushed further and further to the left of the diagram, closer to the operational system, everyone here knows what I'm talking about, it's not necessarily a bad thing, because you'll just never get that exact point in time from the analytics system itself. And so, again, there's no app changes here. On the exact same cluster that's feeding you C#, Java, JavaScript, whatever app that's pounding it, you could also open a BI tool and say what's going on. And the intent of having the cluster is that you've got the resources available to do that, rather than putting pressure on a less scalable single node system. Okay, last set of demos here, and then we'll keep moving. Let's go back to duplicate. We'll go get my PG admin again. Demo 4, drop the tables. This is getting a little repetitive. I'm sorry, but we're pushing the message home. We'll create customer to be distributed again. We'll create sales transactions. We will create distributed table. I don't need to show you. You trust me that they're distributed by now. We'll insert some records into customer. We'll insert a few more records into sales transactions. And then we'll go run this query. Let's stop for a second, because I moved through that quick. We sharded sales transactions on tenant ID. We sharded customer T on tenant ID. These tables are aligned. let's go run this query where I'm going to join on tenant ID and customer ID. Important point that I haven't made yet, although you saw it in some of the earlier demos. So long as my shard key is present in my join, and it's an equality join, greater than or less than is not going to be a good situation here. It's an equality join, then it doesn't matter how many other things you've got in the join. It's kind of like group by as well. So long as the sharding key is in a group by, with a whole bunch of other columns, it doesn't matter. We will localize that within the node. And here is my filter on tenant ID equals 1. So remember I showed you the plan before. If I go run this, this means that that 1 at the bottom means we've been able to localize the join and the filter, or more to the point, we've localized the join onto a single node because the filter tells us, based on our shard keys, that all of the data is on that node. And needless to say, although I didn't plan to make this part of the demo, and things can always go wrong, if I drop that again, we've got no idea where this data is. We know it's we know it's in all of the shards. And so there's the 32 again. What if, and I'm just going to go wax lyrical here because I didn't plan to do this at all. What if we went in 1 and, I don't know, pick a number, 100. I think this works. 2. Now, if I play with this long enough, I'll find another value that's in the same shard as 1, and we can get it back to 1. But it did what I hoped it would do. Statistically speaking, 100's going to fall somewhere else. Okay. So let's go clean that up. And that is sort of the end of these demos. I will skip that one. I'll just show you this statement here. This is the statement, by the way, to turn on repartitioning joins, by the way. So it's set to false at the moment. Well, this says false. It's actually turned on at the moment. But if you're trying to do a shuffle because you're joining across non-aligned columns, then you need to turn this on to be true. What's written on the screen will be a session level. If I put in alter database foobar at the top, that'll be a global setting in Postgres. Okay. Let's go back to extending and slides. We did the demo. There's actually 3 classes of app that I'm not showing. I've only got 2 here. Multi-tenant SaaS app, sharding on that tenant is beautiful. There's a lot of customers doing this today on Cosmos DB. It's stunningly scalable. I gave the example before around small nodes with lots of IOPS. IoT, real-time apps, right? Just pushing records in through event brokers and things like that are really valuable. The third one that's missing here is just your run-of-the-mill good old enterprise app. The reason I left it off here, it's a little harder to join because you've got the reference tables really come to the rescue there. But the big second point I want to take away aside, the first one was the guarantees of sharding. The second one I want you to take away is that monolithic data models do not work for all of the reasons that I've given you today. There's a whole bunch of goodness, tons of goodness. It's why I advise start on small nodes with distributed models. But if you're picking up a big sort of model that's been built over time on a traditional single node system where no one has ever considered the implications of creating unique keys and foreign keys between these tables, as I've shown don't work, you will have some rework to do. My view is that generally things are worth it. Okay, what happens when things slow down? Over time, data accumulates at different rates. And when you've got 32 different buckets of data, they'll all start even with 0. And over time, someone does more than something else. So what happens when shards get too big on one node than another node? Well, you get a hotspot, obviously, because all of these nodes are equal size. We only support homogeneous size compute nodes. There have been asks for heterogeneous size worker nodes, maybe one day. But right now, they're all the same size. There are database functions in the database itself that you can run that will online rebalance the nodes to balance the compute, right? Wonderful. So the biggest disaster you can actually get into being imbalanced is if you start to run those fan out queries, right? If one node is hot for those singular shard queries, then 1/6 of your user base is getting a slightly slower experience. Not great, but not the end of the world. But if you start to run fan out queries, you can't get the result back until every node gives you back its data. And so that's why you want to try and stay relatively balanced. I think what's even cooler is shard level. I could have a tenant level isolation. Imagine I've got my 32 shards each, and let's say I've got 32,000 customers for the sake of simple maths. So I've got about 1,000 tenants or 1,000 different tenant IDs in each shard. And one tenant gets big. I don't know why. They get big. They're active on social media. They're sending more emails. They've got more devices in their IoT system or whatever. Tenant isolation enables you to break that shard apart based on the value of the tenant. And I'll show you a video of this just to make it go a bit quicker. And then move that tenant explicitly to another node. And then we effectively affinitize it there so that when you scale, it will always keep its own node, right? These are first-class features of the database engine. You write SQL to go do this. And for people who write SQL, like me, and I'm sure like you, that's generally pretty interesting. So let me show you how this works. I'm going to hit play on this video, and I'm going to basically verbally annotate it while you watch it. This is one that I've done before. It's online. I'm just going to mute that quickly and hit play. Play? There we go. Okay, so I run an app. The app is running. There's tons of traffic hitting the database. PG admin. I've got 3 worker nodes, 0, 1, and 2. And I'm going to take a look at my shards. And in my shards, you'll see that actually I've got some shards on the coordinator, but this node name where each of the 32 shards is, there's no worker node 2. Tenant 201 is big, 70,000 rows, disproportionately larger than all of my other nodes. And so here we're going to run this function, isolate tenant to new shard, based on value 201 itself. So this runs online, app keeps running, inserts and updates running. We go look at the side of shards, scroll to the bottom, and here's my new shard. You can tell over here, it's blocked by the scroll, but this is the biggest shard right here. And it's sitting on the coordinator at the moment, which is not really what we want. So now, mouse is a little slow. We're going to go down here. We're going to run another function, Citus move shard placement. And I update some values here. I take the shard ID. I'm going to take the node that it's on, which is C. And I'm going to give it the node I want, which is W2, right? Which is the new node that I showed at the top. So I'm going to run this. This is physically moving data in the cluster. The app keeps running and never stops. Now we'll take a look at my side of shards again. We'll scroll right to the bottom. And there's W2, dedicated new node in the cluster. App kept running. No connection string change. No app modification. No anything. And so you can see now the simplicity of scaling the cluster while the app runs using first-class features in the database. This is the closest thing to like commentating live sport that I can figure out how to do with a database. So I hope you appreciate the timing that went into that rehearsal. Okay, let's keep going. The enterprise readiness of it. So one of the interesting things about Cosmos DB is that Citus is built on open source. And so you can download Citus and install it on Postgres on your laptop in your data center, and you can build on it. I guarantee you that the code you write there, you can cut and paste into Cosmos DB because Citus is the same engine, and my team works on that. High availability is in the system. Synchronous replication with an RPO of 0 to automatically fail over across availability zones is in the system. We support built-in monitoring in the system, which is obviously no-brainer. You would expect that, so not a lot to say there. We support private link, which is effectively mandatory for any enterprise deployments of any database system in the cloud today. And I want to finish just quickly with the bonus demo, if you don't mind. So I'm going to go back to duplicate here. And I'm going to bring up this guy. And I'm going to put him over here. And I'm going to just jump back into the Azure portal. All right, so what are we going to do here? Let's take a look at what the actual node utilization looks like. I've got a demo app here, different demo app, but you notice I kind of like using this sort of split screen thing. Let's get some traffic going. Where's my SQL bits? Go. This app is actually more intensive than the one that I showed in the video demo. This is actually calling stored procedures in Postgres. Some of them are doing joins, some of them are doing inserts, some of them are doing updates. Each of these queries individually takes between about 100, actually the insert takes about 30 milliseconds. The queries range from about 100 to 500 milliseconds, right? And I'm spinning up actually 16 asynchronous threads just in a C# app and just bombarding the database. And here I've got the monitoring on the right-hand side. I'm going to clear a couple of filters here and just show you exactly what I'm doing. So we'll start by adding a metric. Hopefully that's big enough. So we'll add a metric, CPU %. And we're pretty low here because the monitoring hasn't caught up yet. Let's take a look at the last 30 minutes here. This app, by the way, is running off my laptop connected directly to Azure. So kudos to the Wi-Fi in this building. It was high risk. I'm going to add, so we'll wait for this to kink in, but I want to add a filter and the server name. This is a 4-node cluster. And so if I take a look, you can see I've got my coordinator, and I've got worker nodes 0, 1, 2, and 3. Right? These are all fixed. You saw in the demo before it had 3 nodes. And so let's just take a look at those worker nodes only. All right, we're starting to get a little bit of a bump here. All right, I don't know what I did there. I didn't mean to do that. We're climbing. Now we're going to climb much higher. Right? This app is geared on 4 nodes to run at around about 100% CPU utilization on each. So we'll give it a split second here, and maybe we'll refresh it. But what's also interesting is you can apply splitting here, and I could take the server name, and that'll just split it automatically. And so here you can see we've just got a little bit of lag in the monitoring, but I can see the performance of each of my worker nodes. I'm tying this back to the live video demo I showed you before, right? Here you can see the utilization of each worker node. This is your sniff test as to whether your application is getting imbalanced in the distributed system. Once you've done that, then you go run the SQL queries to find where the heavier tenants are. Then you can run the tenant splitting that I showed you in that video. We are working on a feature right now, which I can tell you about, called tenant level monitoring, which based on the utilization of rows in a table will tell you the utilization. So not server monitoring, not database monitoring, effectively row level monitoring in the database itself. And so the round of applause over there and the round of applause over there and the 5 minutes here tell me that I'm right on time. So I'll hit refresh one more time to see if we can get, there you go. On the left-hand side, we're up to about 100% utilization. So we're really working this cluster. And if I really quickly just flip back to close out this demo, I'm going to go back to good old PowerPoint, which I've got here. And if I just hit this one, the getting started references, there's a free getting started, aka AMS, try Cosmos DB, is free to get started for 30 days. You can extend it, almost full functionality, except tons of scalability, as you would imagine. But you don't need an Azure subscription. You can just go. And then we made it generally available in October of last year. We launched it at Ignite. There's a ton of stuff that's going to be rolling off the belt in the next 3 to 6 months. And I hope you enjoyed the session. Enjoy SQL Bits. Thank you.